Hello and welcome to our second lesson on evaluating limits, where today we're looking at the change of variable technique. Today's lesson will be a bit short as the material itself will require a lot of practice, so you have a practice set to work on as well as some additional questions and some other resources for you on Google Classroom, so please check those out and let's jump into it. So today's learning goal is that you're going to be able to evaluate limits algebraically using the change of variable technique, and you're also going to analyze the behavior of the curves depending on what the expression that we're given looks like. And we're going to make connections between the algebra and the graph. So let's look at our first example here. We have um, our function here, x minus 1 over square root of x minus 1. As always, we try by direct substitution first, and right away I can see in my denominator, square root of 1 minus 1 is 0, so that's my indeterminate case, and we see here that the numerator is also 0, so we do get that 0 over 0. Since I have a square root, I'm also going to, from last lesson, attempt the conjugate to try to rationalize the denominator. And so here the conjugate is square root of x plus 1. And if you try to multiply this, I'll just set it up to show you. If we multiply this in our denominator, we're going to get x minus 1. And given that our limit is x approaches 1, I still have that my denominator is going to be 1 minus 1 is 0, so that's still not what I want. So this is now a case where the previous methods we've seen so far is not going to work, so we need to do something else, and that's our change of variable technique. So for the change of variable, we're going to introduce a new variable. Often you're going to see u as the change of variable, and we're going to let that square root equal to u. So that's what I'm showing right here. And now if I square both sides, I'm going to get u squared is equal to x. And the reason why I do this is because I have an x in my expression, so I want to be able to write all my possible values of x as u. And so doing this step right away simplifies my work a little bit when I'm substituting u into the final equation. So um, yeah, make sure you always start with that and analyze your expression to see which terms for x you have and create equivalent expressions using u. Now, when you're doing this, you also have to consider the domain of the original function as well. And considering we have a square root of x, we know that we have to have this be greater than 0, and also that x itself is actually here greater than or equal to 0 because we have that square root. So for this to be defined, we only look at values of x that are equal to or greater than 0. And so subsequently, given that u is equal to square root of x, and this is just a matter of working with inequalities. If you take the inequality of both sides, we're going to see that u is also greater than or equal to 0. And this is going to help us with especially making those connections to the graph, but also because when you rewrite the limit, you now will have to write your limit as u. And so we need to know what values of u we can work with. So now as we rewrite this, so starting with my original expression, and now I'm just putting that u squared instead of x and u itself instead of square root of x, and everything else has stayed the same. We have that negative 1 in the numerator and denominator. Now, here I've already shown you this, but here we're just interpreting that. So our original limit was as x approaches 1. Now, considering the square root, that is now square root of, and again, this is just taking that square root here, similar to the inequality. Then we have square root of x is also approaching 1 when x is approaching 1. And so u, which was square root of x, is also approaching 1. And that's why we have that written in our limit here. Now, again, I'm going to see right away that in my denominator, I have 1 minus 1, which is 0. So right now you might be thinking, what was the point of all of that? But Now having u there is going to help us be able to simplify our expression similar to what we were doing last lesson to get out that factor that's making our expression zero to be able to solve it by substitution. And in our numerator, we have u squared minus 1, which is that difference of square. So we're just going to write that as u minus 1 times u plus 1. And now I can see that u minus 1, that's creating that 0 in my numerator and denominator, can actually be canceled out. And all you're left with now is u plus 1, which, given our limit of u approaching 1, we just solve through substitution to get 2. And so that will actually be the limit of the original function as well. And I'm just going to show you this on the graph. So here I've graphed my original function of x minus 1 over square root of x minus 1, and that's shown in blue. And again, you can see that domain of x is greater than or equal to 0 because that's where the function is defined. And you'll see that red dashed line is our x equals 1, a straight line, our vertical line. And if you look closely, we can see that as the function is approaching that value from the left and the right side, then we are actually approaching that value of 2. And again, there's no point of intersection here. And the reason for that is because the original function is not defined for x is equal to 1. So actually, in my function here, when I'm analyzing the domain, it would actually have been useful here to have also x is not equal to 1. And we saw that this didn't really affect our limit. We were still able to analyze it because, again, we're considering the behavior, not necessarily saying that x would be 1 or u would be equal to 1. We just want to know for values close to 1 from either the right side or the left-hand side, what is the behavior of the curve? So what value could we be approaching? And we saw that it would be 2. Now let's look at another example here. Now we have a different type of root here. We have our root of 6. So x to the power of 1 over 6, this is the same as root of 6 of x. And right away, similar to above, by substitution, we have 1 minus 1 in our denominator, which is not going to work. So we need another method. Now, similar to the example above, we're going to see that rationalizing doesn't really help us here. So we're just going to skip right to change a variable. So now here, again, we're focusing on that root because that's the one we want to get, that's the term we want to get rid of. So we're going to let u be equal to x to the power of 1 over 6 or root 6 of x. And now, taking the power of 6 of both sides, we have u to the power of 6 is equal to just x. And again, we do that because I have an x term there, and I want to know how I would write that as u. And for example, if you had x squared, then you can always start with this just to get that x value because it's always helpful. And then you would have had to do x squared is equal to u to the power of 12. And that's the term that you would use in your expression. But we don't have that here, so we're just going to work with u to the power of 6. Now, here again, because you have that root of 6, we know that we have to have a restriction on x, which is that x is greater than or equal to 0. And so consequently, u is greater than or equal to 0 as well. Now, rewriting this expression again, in terms of now u, we have, start with your original, just to make sure you're matching it correctly. And so x to the square, or sorry, to the root of 6 is now u minus 1, and x minus 1 is now u to the power of 6 minus 1. And notice here I've already written my limit as u is approaching 1. And the reason for that is as x is approaching 1, we have that root 6 of x is also approaching 1. And so we have u is approaching 1 because those two are the same. Now, again, u is approaching 1. In my denominator, I'm going to get 1 minus 1, which is 0, so that doesn't work. So now we have to factor. And this is just going back to the methods that we learned last class to see which one now works. So here, this is it's actually a difference of squares where so a squared minus b squared, remember? Now a here is just u3. And so using that formula for difference of squares to factor, we have u3 minus 1 and u to the power of 3 plus 1. And now, this one itself, the first term, u to the power of 3 minus 1, is a difference of cubes. Because, again, 1 cubed is just 1. And so using that difference of cubes formula from last class, we can write this as u minus 1, and then we have u squared plus, this is actually u times 1, which is just u, plus 1. And then we just have that u to the power of 3 plus 1 left over. Now we have those two common factors there that, again, are making that indeterminate form of 0 over 0. So we're going to get rid of them. And now in my numerator, I'm just left with 1. And in my denominator, I have an expression that I can actually work with. Because now here, we have 1 plus 1 plus 1. If we substitute u approaching 1, so just u is equal to 1. And over here, u cubed plus 1 is just 1 plus 1. So I have a denominator that I can work with, and putting all of that together, you have 2 times 3, which is 6. And so the limit is actually 1 over 6. And similar to above, I suggest you try to graph this and see this for yourself, that the curve will actually be approaching 1 over 6 as u or x is approaching 1. Now we're going to see another example. So here we have the limit as x is approaching 0 of x plus 8 to the root of 3 minus 2 over x, where that denominator already tells me that it's an indeterminate case. So here, we're now going to let that cube root be equal to u. And this one is actually different from the ones we've seen so far because here, or actually it's similar to the one we saw in A, because we have something. Oh, sorry, no. This is different than the ones we've seen so far, because here the cube root itself has two terms. It's x plus 8, whereas in A and B, we just had we started with the square root of x, and then we had the root 6 of x. So in my roots itself, I just had x. But here it's x plus 8. So this one is actually can be written like that. So we're going to see, and I'm going to ask you now to think what difference could this make in working with change of variables? At what point do you think that plus 8 is going to make a difference for our solution? So again, start with defining your variable u, and here we're going to let u be equal to the cube root of x plus 8. And now, when we take that cube, we have x plus 8. But that's not the x that I was looking for. So we have now x is equal to u cubed minus 8. This is just rearranging it, but it is going to make a difference for us when we look at the limit. So keeping in mind that we started with our limit of x is approaching 0, now having this new definition for u, or this new variable u, we will actually find that this is going to be approaching 2. The reason for that is if we have 0 here, which is x approaching 0, then 0 plus 8 is just 8, and the cube root of that is 2. So now when we're rewriting our limit, we have a different limit, which is u approaching 2. In the examples above, x was approaching 1 and u ended up approaching 1 as well. But here, x is approaching 0, but u is approaching a different value, which is 2. And again, that goes back to that plus 8 there. So that's where we have that difference. And the rest is just going to be the same. So we're rewriting now. Start with your original function here. So just rewrite now as u approaching 2. And then we have u minus 2 there. And my denominator was just x, which we did evaluate up here. We solved it by rearranging to get x is u to the power of 3 minus 8, or u cubed minus 8. And now this is equal to, and you'll see again that here we have that difference of cubes. So using that formula, we can factor out, and there's that term that's making or giving us the 0. Cancel those out. And we are left with 1 over u squared plus 2u plus 4, which you can now solve through direct substitution. And we get 1 over 4 plus 4 plus 4, which is 1 over 12. Okay, now we're going to look at another example here. And this one now has a square root both in the numerator and the denominator. And so here we have a root of 4. So as x is approaching 16, that denominator is going to become 2 minus 2, which is 0. And if you try multiplying by a conjugate to rationalize, it's not really going to work. So we're going to attempt change of variables here to see how it's going to look like. And the difference here from the other examples we've seen so far as well, in the other examples you had like x at one point, so when you had your change of variable, you wrote it as an expression of x, but here we don't have x, so we have square root of x, so we're going to see how that makes a difference as well. So first, define your root of 4 of root 4 of x as u, and that's our new variable. And now, raising to the power of 4 on each side, we have u to the power of 4 is equal to x. And now, because I want that square root of x, because that's the term that's in my expression, I just take the square root of both sides of this expression. So I did actually write it in terms of x first. And as I mentioned, that sometimes helps simplify or visualize it a little better and help you figure out what next step you need to get to the term you actually need. And the term we actually need here is that square root of x. And now taking that square root, we have square root of x is equal to u to the power of 2, or u squared. Now, we have to analyze our limit. So here x is approaching 16, which means that u, which is the root of 4 of x, is going to be approaching 2. And that's just substitution and evaluating. And now we're going to rewrite our limit in terms of u. So starting with our original function, we now write it as limit of u approaching 2 of the expression u squared minus 1, u minus 2. So this is just those two u's substituted, and everything else is the same. Oh, sorry, this should not be there. Okay, now if we inspect the numerator, that's a difference of squares, which can be written as u minus 1 times u plus 1. But if you look at this now, I still have that u minus 2 in there, and I can't get rid of it. So I can't simplify it, and that means it's still an indeterminate case. So what does that mean for us? We can't really actually evaluate it, and you would stop here. So your solution is complete, but now let's interpret what this means and what it could look like. So here I've actually graphed the function for you, and it's shown in blue. And the red line is x equals 16. And you can see that the function doesn't actually reach any specific value as x is approaching 16, or in the change of our variable as u was approaching 2. So here we have an asymptote. So you see that um, from the right-hand side, we're going infinitely um, up. So we're going towards positive infinity. And from the left-hand side, we keep decreasing and we're actually approaching negative infinity. And so not only is it not defined because it has those infinities, but we also see they're also going in different directions as well. So here, that would be your solution, and we would just say that the limit is undefined. And the reason for it, as you're seeing in the graph, is because it's an asymptote. So there's no actual value. Um, So there wouldn't be an actual value. Now, if we had that we're approaching positive infinity from both sides, we could maybe interpret this as the limit is approaching infinity, but we don't have that. We have that there on one side we're approaching positive infinity, and from the other side we're approaching negative infinity. So we can't even make a decisive conclusion there because they're different limits. And if you remember from what we learned about limits, you need the right-hand side and the left-hand side to match for the limit to be defined. Now, let's look at an example with absolute value, because absolute value is a special kind of function as well, and we have to analyze the domain here. So here, given the limit of x approaching 2 of this expression here, you can see right away it is an indeterminate form for the numerator and the denominator, because you would just get 0 over 0. And we're also going to then make connections to the graph of this. So consider this, we're going to define it as a function f of x, which is defined as such. So here we have to analyze if x is greater than 2, as well as when x is less than 2. And I want you to think for a moment why we don't consider x is equal to 2. And that has to do with our denominator, because x is not defined. So generally with absolute value, you would be looking at both sides. But here, because of that denominator, we also have that it's not defined for x minus, or x is equal to 2, because of that x minus 2. So in our domain itself, we don't have x equals 2, so we don't have to consider it here. Now, splitting this into when x is greater than 2 and when x is less than 2 to get that value of the absolute value, we can see that when x is greater than 2, we will have 1, because those two, the numerator and denominator are going to simplify to just 1. And in the case when x is less than 2, we have the same thing, but with that negative there, because we have to consider that our values would actually be negative. And so that is actually -1 there. Now, looking at the function here, or the graph of the function here, we have two straight lines, and we have those two holes because x is not defined for, the function is not defined for x is equal to 2. And so we see here that the right-hand limit and the left-hand limit are also not the same here, because on one side you're approaching 1, and from the other side you're approaching -1. And so the limit also here does not exist, but for a different reason. It's not an asymptote here. We just have it being two different values. So the left-hand side and right-hand side limits are do exist, and we can evaluate them, but they're just not the same. So again, by our definition of limit, our overall limit does not exist. And finally, let's look at one last example, and we're again talking about existence of a limit itself. Now, here we have the square root of 9 minus x squared, and we want to find the limit of x approaching 3 from the left-hand side because of that negative. So we know that for this function, we already have a restriction on the domain and range. So our domain has to be, so values of x, X has to be, or perhaps let me rephrase it. We know that the square root itself, which is f of x, so your range, has to be greater than or equal to 0. So we have this. And for this to be true, we also require that 9 minus x squared is also greater than or equal to 0. And this is just the same as saying x squared has to be greater than or equal to 3. Okay, so consider, for example, when, or sorry, this has to be 9, and then we can say that x itself is between -3 and +3. And consider, for example, when x is 4, then you're going to have 9 minus 16, which is negative, and you can't have a square root of a negative. So that's our restriction on the domain and the range itself. And now, from this domain, we also have to go back for our range because when we already have this restriction for the domain, consider when we have values of x in that range, then f of x itself is actually also has another restriction, which is that it's between 0 and 3. And the reason for that is the maximum value you get for the output is when x is 0 and you get just square root of 9, which is 3. And now let's make those connections to the graph because that's exactly what we can see here. So this is our range going, or sorry, our domain going from -3 to 3, and our range, which is between 0 to 3. Now, remember our limit was the limit of x approaching, um, or sorry, my bad, this should be -3 there. So as you're looking at x approaches 3 or -3, from the left-hand side, we see that our function is not defined for those values. So when your domain is not even defined there, there's nowhere for me, no, like I can't follow the curve here and reach those values. And considering given those table of values that we were working with, I can't input any values of um, x approaching -3 from the left-hand side because it's not in my domain. For example, -3.01. That's not in my domain, so I can't consider that. And so, again, these should be -3. I'll fix that for you on the updated handout, but you're going to see that this limit does not exist because it doesn't exist on the domain. And so that's why it's important to always analyze your domain as well, because it does actually affect your limit. And so now you've seen, oh, and yes, there we just have some making connection questions. So you can also make that conclusion now from, and this one's actually correct. You can also make that conclusion of why we cannot have the limit of x approaching 3, so x approaching 3 from the right-hand side. Because again, we don't have that to be defined in our domain. So we don't have 3.01, for example. So I can't consider what those values would be. And finally, what can you conclude about the limit of x is approaching 3 here? Then we can say that because the limit is not defined, then sorry, I have to update that for you as well. Because the limit is not defined from both sides, then we actually don't have a limit at -3 or 3 because, again, we don't have a left-hand side and a right-hand side limit. We just have one of them for each. And so, yes, now you've seen a lot of different ways for how to solve limits, and especially this lesson with change of variables. Please make sure you get lots of practice with it. So I have some practice questions here for you, as well as a practice set on Google Classroom. So please check those out. And as always, if you have any questions, don't hesitate to reach out, and I'll see you all next class.